Hi everyone, hope you're doing well. So the sort of final lecture, I guess, in this case of term is going to be on time travel, which was the most popular topic according to the survey that I did, and it's quite an interesting one and fun one. Um, I'm going to follow the same format as with the last online lecture, which is to base it around the handout that's online, to elaborate and explain that. And so hopefully it will add something to simply doing the reading or reading through the handouts on your own. So when it comes to philosophers and physicists and philosophers of physics talking about time travel, there are at least three questions that we might ask relating to that possibility. So we might ask whether it's time travel is logically possible or metaphysically possible. That is to say, roughly speaking, whether it's coherent and consistent, the supposition that it should occur. A second question is it physically possible? That is to say, is it compatible with the laws of nature that hold in our universe? Now, you might think, and many philosophers do think, that something doesn't have to be physically possible to be logically possible. So the idea is that it's logically possible, it's not incoherent, that there should have been different laws of nature, for instance. So the notion of a Newtonian world is logically possible, even though we now know that our universe doesn't follow the laws of Newtonian mechanics. So even if we find that time travel is logically possible, we might still wonder whether or not it's physically possible. We might wonder or not whether it's compatible with the laws of nature as they actually are. And there's kind of a third question, which is, could it or does it really happen in our universe? So now you might think that, so the idea here is that possibly even if the laws of nature don't rule out time travel, there might just not be any in our universe. And we'll sort of see an explanation for why that might be. But roughly the idea is that there might be certain contingent, that is, non-lawful facts about the actual universe that mean, just as a matter of fact, rather than as a matter of law, there happens to be no time travel. So we'll see that facts about the actual distribution of mass energy throughout the universe may rule out time travel in our world, if the general theory of relativity is correct. Okay, so I mean, obviously, if you think time travel does happen, then surely it implies that it's physically possible and logically possible. And likewise, if it's physically possible, even if it doesn't actually happen, presumably that implies it's logically possible. But the reverse entailments don't seem to hold. So the fact that it's logically possible doesn't imply, one normally thinks, that it's physically possible or that it really happens, right? Just the fact that it's coherent doesn't imply that it's compatible with the physical laws or that there actually is time travel in our universe. So, I mean, I suppose because, this is really a course on space and time, rather than just a straightforward metaphysics class, it's interesting to look at actually the extent to which, and maybe focus a little bit on this, the extent to which time travel might actually be physically possible. And this is a possibility raised by general relativity. So I won't get too technical here. So general relativity is not one of the topics we covered in a seminar. And I won't, presuppose that, and I won't expect you to get into the technicalities of general relativity if you write an essay on this topic. But if you're interested in finding out a bit more background, obviously the reading and handout for the general relativity topic might be worth taking a look at. So, interestingly, general relativity holds out this apparent prospect that time travel might be physically possible. So it seems that time travel might actually be compatible with the principles and laws of general relativity. So, in particular, general relativity is at least partly characterized by what are known as Einstein's field equations. So Einstein's field equations essentially say how the curvature of space and time, or space-time, I should say, depends upon the distribution of matter and energy within space-time, among other things. So the idea in very general, broad brushstroke terms is that general relativistic space-time differs from either Euclidean space-time, Galilean space-time, or indeed the sort of Minkowskian space-time of special relativity, in that mass and the distribution of mass makes a difference to its shape. And in particular, the idea is that gravitational effects are actually explained in terms of the shape of space-time rather than some straightforward force of attraction. The idea roughly is that the effect of mass is to bend space-time. So the analogy that's often used is of, imagine a rubber sheet that's going to figure as a model of space-time, and imagine putting something like a bowling ball on a stretched out rubber sheet. Then obviously, so that the bowling ball represents a concentrated mass. Then the effect of that bowling ball is to distort the rubber sheet, and the idea is that because space-time in the role of the rubber sheet is distorted at that point, the tendency is for other objects to roll towards the indentation or depression caused by the bowling ball, and so that's a sort of an analogy for the explanation of gravitational attraction in general relativistic space-time. Okay, so what's interesting is that it seems that the field equations, which say how the curvature of space-time or the shape of space-time depends upon mass energy, appear to be compatible with what are known as closed time-like curves, or sometimes called CTCs as an abbreviation. What is a closed time-like curve? Well, a time-like curve is a trajectory through space-time, so you could think of it as a world line or something like that, such that the speed of light is never exceeded along this trajectory. So an ordinary object, could travel along this trajectory. It could genuinely be the world line of a regular object because following the trajectory doesn't require at any stage traveling faster than the speed of light, which we know is a limitation on the speed at which ordinary objects can travel. So a closed time-like curve is a trajectory through space-time such that an object traveling along it would never exceed the speed of light, but after a certain amount of time, the object would revisit a space-time point that it had previously visited. So it could go back to where it previously was in space-time without at any stage traveling faster than the speed of light. So in other words, you can think of a closed time-like curve as a loop in space-time, so where you can return to the position in space-time that you've already been to. So the idea is that each event that occurs on a closed time-like curve, so, suppose I were to somehow travel along a closed time-like curve, and I were to give this lecture, then the idea is the event of my giving this lecture would lie both in the absolute past and the absolute future of that very same event, right? So my giving the lecture would lie both in the absolute past and the absolute future of my giving the lecture. And generally, each event on a closed time-like curve lies in its own absolute past and absolute future. And this is sort of, by analogy, we could think about the way in which, on the surface of the planet Earth, each object's both very far west and very far east of itself. So the idea is a closed time-like curve is analogous to the sort of curved space that comprises the surface of the planet Earth. Okay, so there are a couple of ways in which Einstein's field equations are compatible with the possibility of closed time-like curves. So basically, in order to get closed time-like curves out of Einstein's field equations, you just need it basically depends on a couple of things. So firstly, it depends upon how mass energy is distributed in the universe. So whether it's distributed in the right way to curve space-time back on itself. It also depends upon what's known as the intrinsic curvature of space-time. So whether and to what extent and in what way space-time would be curved in the absence of any mass energy. So I guess with the rubber sheet, it seems possible that the rubber sheet should be flat if no massive objects are placed on it. But it might also have an intrinsic curvature, maybe either convex or concave. And this would be its intrinsic curvature. So whether or not we get a closed time-like curve depends both on the intrinsic curvature and the distribution of mass energy. Now, it turns out that there's sort of two, given the right intrinsic curvature and the right distribution of mass energy, we could have one of two sorts of closed time-like curves. So it might be that the sort of whole universe, in a way, curves back on itself. So it's the spatial analog would be the surface of a globe. So the whole of space-time would be structured like the surface of a globe, so that each point in space-time lies on a closed time-like curve. That is to say, you could travel back to that very same space-time point without ever traveling above the speed of light, and that would go for any space-time point. But other intrinsic curvatures and distributions of mass and energy would give rise to a structure that involves not this sort of global curving back on itself, but rather what are known as wormholes. So a wormhole would be kind of a region of space-time that forms a closed time-like curve, which is constituted by closed time-like curves, without necessarily the whole of space-time having that sort of globe-like structure. Okay, so the wormhole, only some parts of space-time would have closed time-like curves running on them, and so I suppose then the sort of idea would be that maybe this could model something a bit more like classic time travel stories, in the sense that if you had a wormhole located sufficiently close to you in space-time, then maybe you could take your rocket ship and fly into that region and embark on this path that would take you back in time, back along the t-axis of your space-time. Now, okay, so this sort of existence of closed time-like curves will give rise to this sort of the possibility of a sort of time travel. So this is sort of interesting because it implies that time travel is potentially possible in sense two, right? So it's physically possible, it's compatible with the laws of our universe. Now, presumably, we might think that, well, if it's physically possible, it must be logically possible. Actually, we'll see some arguments that aim to show directly that it's not logically possible. So then we might think, well, maybe we've gone wrong in supposing it's physically possible. Maybe we were mistaken because, it seemed that if it were physically possible, it would have to be logically possible. So the arguments that it isn't logically possible might cast doubt upon whether it's physically possible. Another point to note before we go on is that the fact that it's physically possible, in the sense that it is compatible, assuming it is, with the laws of the universe, in particular Einstein's field equations, doesn't necessarily imply that it actually happens in our universe, right? Because it might be that the distribution of mass energy in our universe isn't right, isn't the sort of right one, or the intrinsic curvature isn't the sort of right one for producing either a global structure in which space-time curves back on itself, or more localized wormholes. So it might be that, although were the distribution of mass energy different, this would occur. In fact, in our universe, it isn't right for it to occur. And it's certainly worth noting that we haven't observed any evidence of wormholes in our universe, and the likelihood of a wormhole sufficiently close to our planet that we could ever travel to it is presumably exceedingly remote. So, unfortunately, if you have aspirations to become a time traveler, it seems rather doubtful that those are going to be fulfilled. Okay, so I said that, so there's at least we have some sort of prima facie reason to think that time travel might be physically possible in light of general relativity. It's more dubious whether it does happen in our universe or could happen given the distribution of mass energy. But there's some interesting philosophical arguments concerning its logical possibility. And as I said, if it turns out logically impossible, then this presumably casts doubt on the physical possibility, or undermines the claim that it is physically possible. So let's look at some of these kind of logical or philosophical puzzles that arise. I suppose sort of a first thing to note is that, as David Lewis points out in his paper that's on the reading list, any plausible sort of time travel isn't going to involve changing the past. So I suppose that in some sort of time travel stories or movies, the protagonists actually get the opportunity to change the past, um, whereas in others, all they do is make the past the way it's always been. Now, Lewis argues that um, changing the past really is logically impossible because the past can't be two ways. One way it was before your intervention, and another way which it is after your intervention. There's just one way the past is, there's no obvious incoherence, Lewis thinks, in suggesting that you cause the past to be the way that it's always been. The existence of closed time-like curves seems just to give rise to this possibility of causing the past to be the way it's always been. If you travelled around a closed time-like curve and revisited the point on it that you've been to, the idea would be that there's no possibility of not travelling around that closed time-like curve at the second time of asking. But we'll come back to that later in the lecture. Okay, so what are some of the philosophical puzzles about time travel? So one puzzle is the puzzle around causal loops, which is close to the sort of thing we've already been describing. So suppose that this is just a sort of an example to get us to think about this. Suppose you're going around in your spaceship trying to find a wormhole. And the world line in this diagram, the world line of your spaceship is represented by the blue line. Now, suppose that someone who looks very much like an older version of you appears in a spaceship that looks very much like yours, but somewhat older. So they follow the green world line, and they pull up beside you and tell you where the wormhole entrance is. So you immediately change course and set sail for the entrance to the wormhole. You then enter it, travel for several years, until you encounter someone who looks very much like you but younger in a spaceship that looks very much like yours but somewhat newer. And you tell them where the entrance to the wormhole is. So the sort of, idea of what's going on here is that you enter the wormhole, the younger version of you, travel around this loop, and exit the wormhole after your travels when you're a bit older and the spaceship is a bit older, and encounter your younger self and tell them where to find the wormhole entrance. Now, this is certainly a very unfamiliar sort of thing to happen and rather puzzling. So you might think, and you might even say paradoxical. So you might think, well, where did the knowledge about the wormhole entrance come from? Right, so it seems that it came from the older version of you who told it to the younger version. But the older version of you only had the information themselves because they were because they had that information when they were younger, and the younger version of you only had the information because they were told by the older you. So the younger you has information because of the older you has the information because of the younger you. So we sort of go around in a circle, a causal loop. Now, so the question is this merely puzzling or merely weird? Or does this actually involve some sort of incoherence or contradiction that might lead us to suppose that actually time travel is not really logically or metaphysically possible after all, and therefore might lead us to doubt whether it's genuinely physically possible. Now, according to Lewis and others, while causal loops are weird, it's not obvious that they involve any sort of contradiction. They're just odd. They're unfamiliar. It's strange that you should get information going around in a loop like this, or a loop of causation. But it's not obvious that that's incoherent or logically inconsistent. So, one way of thinking about this is that we're used to explaining events in a certain way. We're used to explaining events by appeal to earlier events and then explaining those by appeal to still earlier events, whereas here it looks like we have an explanation that goes around in a circle. Now, you might think, actually, there's nothing more weird about that sort of circular explanation than there is about our standard way of explaining things, because our standard way of explaining things might lead to a sort of weird regressive explanation. So you might say, well, why is the universe as it is? The idea would you appeal to some earlier state of the universe, and you might say, well, why was it in that state then? So you appeal to some still earlier state. So either you're off on an infinite regress, or you end up with some thing that explains the later state of the universe, is perhaps the Big Bang, but that doesn't seem to have any obvious explanation itself. So on reflection, you might actually think that, well, maybe this sort of like an infinitely regressive explanation, or an explanation of what happens by something that itself is unexplained, is just as problematic or unproblematic as an explanation that goes around in a circle, which what seems to be the case in a causal loop. So maybe it's just the fact that we're kind of used to one sort of explanation that makes it seem satisfactory, whereas the unfamiliarity of the causal loop type explanation is the only thing that's making us feel that it's unsatisfactory. It's not due to any sort of fundamental inconsistency or incoherence. Okay. So, but there are sort of other paradoxes, or alleged paradoxes, associated with the possibility of time travel. So, the most famous paradox is known as the grandfather paradox. So, suppose that your maternal grandfather is deceased. You have a strong loathing for him because he was cruel to your mother. Suppose that you decide you want to kill him before he can harm your mother. And you decide the best way to do this is to travel back to a time before your mother was conceived and shoot your maternal grandfather dead. Now, conveniently for you, there's an entrance to a wormhole nearby. And the exit of that wormhole is near to your grandfather's spatiotemporal location a year before your mother was conceived. So you enter the wormhole, emerge near to your young grandfather, point your gun at him, and the question is then what happens? Now, you don't kill him, right? You can't, well, we'll talk about whether you can or can't later on, but certainly you don't kill him, because if you killed him, you wouldn't kill him, right? Because if you killed him, there'd be no you, there'd be no your mother, and therefore no you, and therefore no one to kill him. So if you killed him, you wouldn't kill him. So if you killed him, in other words, a contradiction would be true, but obviously a contradiction can't be true, so obviously you don't kill him. So what's the paradox? Well, the paradox is the tension between the sense that, on the one hand, it seems you could kill him, because you've got the means to and the motivation. So, suppose you're very stubborn, you're not likely to change your mind, You've got a gun in working order, you're a very good shot, shot's an easy one, and so on. So everything points towards, it seems, you're being able to kill him. But there's also a sense in which you can't kill him, because if you did kill him, a contradiction would be true, and a contradiction can't be true, so you can't kill him. So Lewis, in his paper, The Paradox of Time Travel, on the reading list, focuses in large part on this paradox. And he actually argues that there's no real paradox here, and so no problem with the supposition that time travel is possible. He says simply that the sense in which you can kill your maternal grandfather before your mother's conceived is just different from the sense in which you can't kill him. So Lewis gives this analogy of speaking Finnish. So he says there's a sense in which he can speak Finnish, in the sense that he has a larynx with the right shape, but there's also a sense in which he can't, right? And the sense in which he can't is because he's never learned Finnish. So his general idea is that when one says one can do something, or in general someone can do something, one is saying that it's consistent with a certain set of facts that one does that thing. But in different contexts, different sets of facts are presupposed, and hence different senses of can. So, in particular, the idea there's no contradiction in saying that something's consistent with one set of facts, such as your physiology, the shape of your larynx, but not consistent with another set of facts, for instance, that you've never learned Finnish. And so, basically, Lewis is going to argue that the grandfather paradox just involves this kind of equivocation on the notion of can, or possibility. So, the sense in which you can kill your grandfather is that it's consistent with facts about your motivation, your ability to shoot, your possession of weapon. But there's another sense in which you can't kill him, and that's because there are certain additional facts with which it's not consistent. Your killing him is not consistent. For instance, the fact that you're his daughter's child and that his daughter hasn't been conceived by the time you aim your gun. So Lewis says there's no contradiction between supposing that you can kill him in one sense, but not in another sense. That is, you can kill him in that it's consistent with a less rich set of facts, but you can't kill him in the sense that it's inconsistent with a richer set of facts, including the fact that you're his daughter's child. Now, of course, you don't kill him, and what you actually do has to be consistent with the richest set of facts possible. There can't be some facts that we haven't presupposed, but that nevertheless obtain, with which it's inconsistent if you're going to do it, because contradictions can't be true. So your killing him isn't compatible with all the facts that there are. It's not compatible with you being his daughter's child and his daughter not having been conceived when you have the opportunity to kill him. And so it follows that you don't kill him. So Lewis suggests that the very fact that you exist just means that you failed for some reason to kill him. Maybe you had a last-minute change of heart, your gun jammed, your shot missed him, some sort of ordinary fact like that. Okay, so Lewis thinks that this is enough to resolve the grandfather paradox. Whether it is or not has been disputed. So again, these papers that I'm going to discuss are on the further reading list. So Vivellin's paper, he considers, well, the example, I'm not going to give his exact example, but I'm going to give a very similar one. Suppose that space-time, in fact, contains lots and lots of wormholes, so that most of the population of Earth, perhaps, is very close to a wormhole that would take them back to the vicinity of their grandfathers before their mothers were conceived. And suppose that there's a group of people, large group of people, are interested in testing out the grandfather paradox. So they form a big society in which each member dedicates themselves to the assassination of their maternal grandfather before their mother was conceived. So this is similar to Vivellin's example. Now, it seems that all of them have got to fail, right? So, because their very existence is testimony to the fact that they failed to kill their maternal grandfathers before their mothers were conceived. So maybe some suffer from last-minute change of heart, some have guns that jam, some miss, and so on. But this kind of seems, Vivellin argues, very strange and like a too big a coincidence, like a cosmic conspiracy. So it just happens that of all these maybe thousands and thousands of people who try to kill their maternal grandfathers, all of them just happen to fail for some reason or other. Now, so you might think that it's just too much of a coincidence to really be possible. You might think that it would have to speak to there being some sort of force or law that prevents them from succeeding. It's worth noting that you can't simply say this law is the laws of logic, because it doesn't seem that the laws of logic can cause your gun to jam or for you to have a last-minute change of heart, right? It doesn't seem that the laws of logic or have causal powers like that. So it seems we need some sort of alternative explanation. And any sort of causal explanation we give for these just makes it look like a big coincidence. Or maybe there's some more normal force in nature. But it just seems very implausible to posit such a force. And you might even think that, actually it's just not possible for there to be such a force. And you might think it's not really possible for there to be such a coincidence. And you might think that a better explanation is that time travel just is metaphysically impossible. So you might think, rather than positing a conspiratorial-looking coincidence or some sort of force of nature, mysterious force of nature that makes these people fail, we should just reach the conclusion that really time travel isn't possible, because this would open up the prospect of this big coincidence or this mysterious force. But then there's still something weird about this, because Einstein's field equations seem to be compatible with this, right? So they seem to be compatible with the existence of wormholes. And you might wonder, so why some solutions to Einstein's field equations would correspond to logical or metaphysical impossibilities, right? After all, our universe just corresponds to one solution. So given the actual value of space-time intrinsic curvature and the actual distribution of mass energy, our space-time is as it is. But surely, there's nothing impossible about the intrinsic curvature, like in a logical or metaphysical sense, about the intrinsic curvature or the mass distribution being different. So why should we suppose that time travel really is metaphysically impossible just because it brings about these, or would seem to raise the possibility of these weird coincidences? So Sider has a kind of third way, or a kind of get out. So he responds to Vivellin's example by suggesting that the case is essentially one of selection bias. So he responds to Vivellin's example by saying that the case is really analogous to one in which you select. So suppose you have this category of lifetime bachelor, right? So a lifetime bachelor is just defined as someone who, I guess, is male and never gets married throughout their lifetime. Now, suppose you selected the set of all lifetime bachelors and asked why none of them succeeded in getting married. Presumably, many of them do nearly get married. Many of them might have been engaged at one time or other. Some might have even made it to the church, but all of them fail for one reason or another. So, they or their spouses suffer last-minute changes of heart and so on. Now, there's no mysterious force that prevents these people from getting married. It's just that we already picked out the ones that did in fact fail to get married for examination. We picked out the class of lifetime bachelors, so by definition they're the ones that fail to get married. The ones who succeed might be just like them, but they're not lifetime bachelors. So it's a sort of selection bias. So Sider's idea is that asking why time travelers fail in killing their maternal grandfathers before they're conceived in an example like Vivellin's is analogous. So the problem is we've selected the category of time travelers trying to kill their maternal grandfather before they're conceived to examine. And of course, these people fail by definition. The fact that they're time travelers trying to kill their maternal grandfathers logically implies they failed, because if they succeeded, they wouldn't exist. Just like the fact that someone is correctly assignable to the category permanent or lifetime bachelor logically implies that they don't get married. Now, so I guess the question is, how analogous are they? So suppose that this universe that Vivellin imagines is one in which lots of people emerge from wormholes and kill men planning on having babies, even though those men are not their grandfathers. So, for instance, they might have different grandfathers, or they might be just people who appeared from nothing, from wormholes, without sort of appearing to kind of enter those wormholes at later times. So the idea is that, in general, plenty of people succeed in killing men planning on having babies. But if we select out of them the class of time travelers planning to kill their own grandfather, then we're selecting a subclass that fails by definition, just as plenty of people succeed in getting married. But if we pick out the lifetime bachelors among them, then by definition we're picking out the ones that fail. So then that might be plausible, but what if there aren't plenty of people spontaneously generating out of wormholes and killing old men, or I guess younger men, planning on having babies? What if it's only kind of the members of this society that harbour these weird ambitions? Then it starts to look cast doubt upon whether really what's going on is selection bias. It sort of starts to look like almost everyone, or perhaps everyone, who tries to kill a man planning on having a baby fails. And then that raises again the question of some sort of cosmic coincidence, which looks very puzzling. So I think there's a lot of room for debate about this example, and it's a very interesting one. What the correct response is. I don't think anyone's really had the final word on this issue. Okay, so I mean, what your response to this issue is might affect whether you think that time travel's logically or metaphysically possible, and then have implications for whether you think it's physically possible, or whether you think that somehow some solutions to Einstein's field equations just don't correspond to metaphysical possibilities. Now, there's another sort of kind of weirdness associated with time travel, or the possibility of time travel, raised by the possibility of wormholes. which also might lead you to doubt whether time travel is authentically possible. So here's an example, sort of example discussed by Maudlin and elsewhere in the literature. So suppose in this example that a billiard ball emerges from a wormhole and hits an identical looking billiard ball, with the result that the billiard ball that is hit is accelerated into the wormhole's entrance. So we have a billiard ball following the green world line that exits the wormhole and strikes a billiard ball following the blue world line, propelling it, changing its course, and propelling it towards the entrance of the wormhole. So, I mean, what we might want to say about this is that actually the billiard ball causes itself to enter the wormhole. And then the exit strikes itself and causes that very thing. So this sort of story seems consistent, right? Okay, so it's a bit weird, right? It involves one of these causal loops, and it's just weird that something should kind of self-explain its own trajectory, its own entry to the wormhole in this way. But maybe it's not incoherent. We suggested that maybe we just might have to get used to these sorts of circular explanations, causal explanations, if genuinely there were causal loops in our universe. Okay, but so maybe that picture's okay, but now imagine another one that seems not to be okay, right? And this is represented by this second picture. Now, the idea in this second picture is that the billiard ball emerges from the wormhole and knocks its earlier self onto a different trajectory than it is on, right? So the idea is emerges from the wormhole, knocks onto this trajectory, resulting in it emerging on this trajectory. The sort of parallel lines are supposed to represent same trajectory. So, in other words, blue world line of billiard ball emerges out, knocking its earlier self onto this trajectory, which is different from the one that it, in inverted commas, first emerged on. And the reason that this is incoherent is because the same billiard ball can't have two different trajectories. It can't have this trajectory and this trajectory. That just seems incoherent. So you might think, okay, well, that's no big problem. But for the reflection, so the setup must be like must be like this rather than like this. Maybe you think it's no big deal, but on reflection, maybe it is kind of a big deal because you might think, well, why should a collision result in the billiard ball being put onto the precise trajectory that it initially is, right? So in general, when two objects collide, I know we're really dealing with one object here. In general, when two objects collide, there are infinitely many sorts of collision that could occur, putting the second object onto infinitely many different trajectories. So why should there be this kind of constraint when it's a self-collision, right? We can see sort of there's a constraint in terms of the logical coherence of the situation. But the case is kind of analogous to the grandfather's paradox, right? It's not like the laws of logic can cause billiard ball collisions to happen one way or another. Laws of logic aren't really a causal force in the world. So you might sort of think, well, why couldn't, what's to stop the causal facts obeying the laws of logic, if you like. So maybe this is sort of paradoxical. Maybe you think, well, if time travel is coherent, then if time travel were coherent, then surely a billiard ball should be able to interact with its past self in any of the ways that a normal billiard ball could interact with another billiard ball. But obviously, this can't happen because we end up with situations that are violate the laws of logic. So it'd be better to conclude that time travel is just impossible in the first place, arguably. So another interesting feature note that maybe makes it even worse for the defender of time travel is that this scenario seems to put constraints on the pre-collision trajectory of the billiard ball. So we're imagining the billiard ball travelling in from a non-time travel region. So it travels in up here on the blue trajectory. It's then impacted by what turns out to be itself, setting it on the trajectory into the time travel region, into the entrance of the wormhole. And we've noted that the only consistent scenarios for a collision like this, where it puts itself onto the trajectory that it emerges from the wormhole from, and not one like this, where it puts itself onto a different trajectory that it first time around emerges on. But obviously, what trajectory the billiard ball is put on depends not only upon the trajectory it emerges from the wormhole on, but also what trajectory it enters the region on from the non-time travel part of space-time. So it depends upon the blue, the initial segment of the blue line, as well as the initial segment of the green line. So that seems weird because we now find that this is constrained. This trajectory is constrained by something that happens later to the billiard ball, namely the emergence of itself from a wormhole, an impact with itself. So we might find it okay somehow that this segment of the world line could be constrained by what happens when the billiard ball emerges. But it seems weird that the billiard ball's, if we want to call it, initial trajectory through non-time travel regions should be constrained by what's going to happen to it at this collision region. So again, to the extent that we find this too puzzling or implausible to be palatable, then we might take this to be a further reason to be skeptical about whether time travel is genuinely logically possible, and therefore whether it's actually physically possible. But then again, so this is the reason there's a lot of room for genuine debate. So are these constraints, such as the constraint not to kill your maternal grandfather before your mother's conceived, or the constraints of the billiard ball's trajectory through the non-time travel region, and also its trajectory from the exit of the wormhole, are these constraints okay, or are they sort of somehow too puzzling or stringent to be tolerable, so that rather than positing that there would be such constraints, we'd actually rather draw the conclusion that time travel is actually metaphysically impossible? In which case, we then face this challenge of explaining why it should be that some solutions to Einstein's field equations, but not others, correspond to what are not genuine metaphysical possibilities. So the debate on this subject is very much goes on, and so for further information, I'd refer you to the further reading list on this topic, as well as some of the readings on general relativity. Okay, so if any of you has any questions about this or any other topic, then, as I've said before, please do email me. And if you'd like to talk some of them through via a virtual meeting via Skype or FaceTime, then please do let me know and we can set that up. Otherwise, good luck with everything. I hope you stay safe and well. And that's it for me. Okay, thank you. Bye.